Hello everyone, and welcome to this PROG1198 tutorial video for week 2. The topics covered in this video are concurrency control and auditing, and they are part of the database administration unit. We've been discussing different ways of maintaining database integrity, and providing things like concurrency control and auditing are just two more techniques in order to do so. So when we're designing our databases, we want to implement database objects and implement our tables in such a way that they reflect the properties and restrictions of the real-world objects that we're trying to represent. So we want to ensure that our designs are robust, that they are as error-free as possible, and that we can protect and control our objects as much as possible. As I've said in a previous lesson, when we're designing databases that are designed to be used by other applications and by a wide range of different types of users, we want to make sure that the database is the most conservative point of validation. So some of the techniques we're going to be talking about today are implementing database objects to allow us to control underlying tables and data, implementing dual key systems, planning for concurrency control, and dealing with basic auditing requirements. Now, we haven't quite made it to database objects yet. Some of the types of objects that we're going to be studying are listed here: stored procedures, views, and functions. Those are just some of the objects that we're going to be learning about. And we're going to be talking more about how those help us design for the real world and how those help us protect and control access to data when we learn more about them. So this lesson is going to focus on these other 3 points: implementing a dual key system, planning for concurrency control, and dealing with auditing requirements. So let's start with the dual key system. The dual key system is a way for us to not only maintain a key that is used for relationships, but also maintain a key that is used for uniquely identifying each record. Now, in previous designs, we've used the same field for both of those, but usually we use a field that represents one of those things really well and sort of falls short of meeting the other mark. If, for example, you consider our employee and department tables from our company example that we've been working through, in the department table, the primary key in that table is a 4-character code representing the name of the department. Now, if the point of a key is to enforce a relationship and uniquely identify the field, then it's doing really well on uniquely identifying the field. That 4-character code allows us to very quickly identify which record we're talking about. But on the other front, being a good programmer's key that's good for handling relationships, that is kind of falling short of the mark there. And the reason for that is because if those are 4-character codes that are maintained by the user and therefore are subject to change because they carry meaning to the record, that means that those fields might be changed. And we know now that if we change a field that's part of a relationship, then we have to determine how the related table is going to respond. So we learned that in a previous lecture when we learned about either we want to cascade or perhaps update a record in a child table when the parent table changes their key. We've seen that in last week's video. Now, the other table, employee, has an identity field. So employees have a random integer assigned to them, and that does really well in performing in a key situation when we're using it to represent a relationship. Because, if you're employee 7 and the 7 doesn't carry a meaning to you, then there's no reason to ever change you to become employee 8. And so therefore, we don't ever need to change that. So that's great for a programmer's key, but it also isn't great for uniquely identifying an employee. That is, you can't tell by saying, who's employee 7? There's no rhyme or reason to who it may or may not be. So Let's take a quick peek at our employee department tables, just so you can get an idea of what I'm talking about. So we're going to select all from department and select all from employee. So our department codes are a great business key, but not so great for the programmers. And employee ID is a great programming key, but not so great for the business rules. Implementing a dual key system is stating the idea that perhaps every table should have both. So under a dual key system, we're saying that every table should have an automatically generated programmer's key that is set as the primary key that is used in foreign key relationships. Most likely we would set that as an integer created as an identity. But also, each record should have a business key. It's there to enforce business rules. So for example, the requirement for a field or combination of fields to be unique. Now, because we can only indicate one primary key on a table, typically we designate the programmer's key as the primary key, and we designate the business key using a unique constraint. So if we want to designate a field to be unique as a business key, say on the employee table, for example, aside from the current employee ID, which we've already determined as a good programmer's key, we don't have anything else here that would be a good business key. So there's no other fields that uniquely identify an employee. And you think, okay, well, what about first name or last name? But keep in mind, we could potentially hire employees that carry the same name. It's definitely a very realistic possibility to think that you might have two different people working at your company who have the same first and last name, especially if it's a very large company. Same goes for title. There's already duplicates here. There could be two people that have the same salary or that start on the same day. So we don't have a good business key here. What we can do in order to create one would be to select a piece of data about the employee that we know to be unique. And if we don't have one, then maybe we need to retrieve more information from our employees. So what I'm going to show you is a way to create a unique business key for each employee. In the real world, this might be something like your social insurance number, or it could be a number that is designated to you based on, your hire date, or a combination of your hire date and your name. At Niagara College, we assign you a student number. That didn't just start counting at 1 and we're counting how many students we have. Those numbers carry meaning, based on whether you're enrolled in a particular year or whether you're a domestic student versus an international student. So business keys really could be anything as long as it uniquely identifies each record. What I'm going to do here is I'm going to create a new column in our employee table that will serve as a business key. Now, I'm going to have to think of a good name for it. Obviously, emp ID is taken. So in this demonstration, I'm going to create a column called emp number. And emp number is something that should be user maintained and unique to each user, but also related to each user record in an identifying way. In order to add a column to an existing table, I perform an alter statement. Alter table and the name of the employee. And I want to use an add command to add a new field. I'm going to provide the name of the field and the data type. But I'm not going to add the constraint right away. The reason for that is because if I create a brand new field without providing any data for it, and then I try to say that it has to be unique, well, having 8 empty fields isn't exactly unique. So I need to make the column first. If there's already records in here, I would need to pre-populate it with something. And then after that, I can add the unique constraint after. So let's create a business key called employee number. And I'm going to set it as a 5-character code. So if I execute this, completed successfully, and now when we look at the employee table, we have this emp number field. Now right now they're all nulls, so I can't add the unique constraint just yet. First I need to fill out the emp numbers for all these employees. Now this is why it's important to think ahead about your design before you move on to the creation. If we had done the design properly the first time, we would have recognized the need for a business key. Had we known about this when we first created the employee table, we would recognize the need for that business key and add it in. And then when we create the employees, as part of the insert statement, we would generate an employee number. But this is kind of going back and bringing it up to speed. And, you don't always get the benefit of perfect foresight when you create something, right? More often than not, you're going to have to create something, work with it for a while, and then go back. So knowing how to alter and change things is a really valuable skill. Okay, so I'm going to give some existing values to emp number. Now, in order to determine what emp number to give each employee, I've just made up some data in here. And so you don't have to sit there and watch me type it. I'm just going to copy and paste. So here are some update statements. So I'm updating each employee record one at a time and assigning a unique emp number to each one. The formula that I selected for the employee number is to use the year of their start date, the last 2 digits of that, so 91 for this person, and then the MGA is generated from the first letter of the first name, first letter of the last name, and the first letter of the title. Now, I could have written a little routine or function to build that up and return it, but as we haven't learned quite yet about how to write functions, I just hard-coded them in here. Later on in a future class, we'll come back to writing a function to calculate what the employee number should be for a given employee. But that's a topic for another day. So let's execute these update statements. We've got lots of rows affected. If we take a look at employees now, each one has their own unique employee number that is a great business key because it is tied to information about that particular employee. Now that each one has a unique value, we want to enforce that future values put into emp number must always be unique. So if I come to insert employee number 9, I can't put in any of the existing values for emp number. It needs to be set as unique. So again, I need another alter statement. Anytime we're changing a table after it already exists, we can modify most things about a table through an alter statement. Another option is you can drop the table and recreate it. However, depending on how large your table is and how many times it's being updated, it's usually more efficient to just change something that already exists. So after emp numbers have all been populated, I want to enforce that unique constraint so that there can never be duplicate values in emp number by performing another alter statement. It starts off the same way. We're going to alter employee, but instead of adding a field, we're adding a constraint. And from this part on, we just write the constraint the same way that we would on any constraint creation, like in a table create statement or anything like that. The syntax from here on is the same. So I type the word constraint, give it a name, and we're going to say that it is unique on emp number. We couldn't have added that before because we had duplicates. We had all nulls. Okay, so we can execute this. Now our emp number business key field enforces uniqueness. So let's take a look here. Nothing has visually changed, but if I try to update the employee and change the employee number to one that already exists, 90NHI, for example, you can see how employee 8 has that one. If I try to assign the same one to employee 1, this is going to be rejected because of the new constraint. You can see that. No duplicate keys. So that's the idea behind a dual key system. Let's move on. Our second topic is concurrency control, and there's a big graphic here trying to illustrate what exactly concurrency control is and why it is such a problem. So in any multi-user system, there will come a time when two users are editing the same record. So what we have here are two users. We've got red shirt and we've got yellow shirt. And both of them are trying to make some changes to the same record. Now they're changing different fields, but the problem is that red shirt has loaded up an editing screen, and she is currently working on changing the first name of Bob Jones. And she wants to change his name from Bob to Robert. While she's in the process of typing the new name, yellow shirt also is trying to edit the same record. Now, she's trying to change Bob Jones's address from 123 Fake Street to 99 Main Road. So they're both working on it at the same time. Now, red shirt is done typing Robert, and she saves her changes, and it is all completed. Meanwhile, yellow shirt's still typing. Now, when yellow shirt finishes and saves her changes are saved with the original name, Bob Jones. She didn't change the name, and the value that she had stored for the first name gets passed back to the database. So when she saves her update to the address, the information that she had about the first and last name are pushed back to the database as well. So what happens here is yellow shirt says, oh, my update worked. Red shirt's already gone out to lunch because she was done a while ago. But meanwhile, the change that red shirt made is lost. The name Bob has persisted because yellow shirt's update overwrote red shirt's update. Now this is the default action of the database. We call it last change wins. And the problem with it is that the red shirt user has no idea that her changes were overwritten. She thinks that it went successfully. She didn't know about the other update that was happening at the same time, and her changes were lost. And that's not even the worst of it. You know, it's one thing if your changes don't work, but the worst part is she doesn't know. So now her idea of the database being a certain way isn't consistent with the reality of what the database actually is. And that's a problem, right? So how can we solve it? Well, we need some kind of way of figuring out when two people are editing it. How do we know? How can we make sure that the record hasn't changed already while you're doing it? So let's compare that then with some of these other options. So here's option 2. We call it compare all values. We can prevent an update if any of the field values have changed since the record was read. Because keep in mind, when you're performing an update, usually what happens is you read the current data, you make a few changes, and then you push all the data that you have back to the database. Now, in this picture, if yellow shirt here compared all values, what would happen is when she tried to save, she would compare the ID, she would compare the first name, and it would flag it saying, hey, wait a minute, the first name that you think you have isn't the same as the first name that's currently there. And it would flag and recognize that change. So the advantage is you can implement this without changing the design of the table. The implementation would happen during however you implemented your update command. The disadvantage, though, is that there's a lot of data being passed back and forth. It is really resource heavy because if you have a lot of field values, or if you have large field values, you could be comparing, 10 or 20 different columns. And if those columns are all, varchar max that hold gigabytes of data, then, a simple save and update command could take quite a while to succeed. So compare all values isn't bad for small data, but it's really not the ideal solution, and it's not the one that we're going to implement in this lesson. Option 3 is version control. So instead of comparing everything, we're going to add a field that keeps track of a row version, and then we can just compare that one field instead of comparing all fields. So how can we implement this? We're going to add one field to the table. You could make an integer that gets incremented. Now you'd have to manually increment it. It keeps track of the version. When you perform an insert, maybe it gets default to 1, and then every time you update that record, increment that value. Now, that would require a little bit of extra work on the part of the update, but that's okay. We're going to talk in later classes, later on in the term, how we can control updates and how they work in the system. Another option is a date time field that you could update. So keep track of the date and time of last read or last updated, and then compare to see if it has changed since you last read it. Or we could do a row version or a timestamp field. And those fields do the same sort of thing, but they automatically update themselves. So we can reject the changes if the row versions don't match. And the beauty of this is now we can inform the user that their change was rejected. So it doesn't prevent that collision, but at least it allows us to trap it and say that it happened. And that's the real difference. Because if two people are editing it at the same time, you can't have the best of both worlds and figure out how to merge it. Those are kind of the slowest, last-ditch effort operations because it requires so much overhead and comparisons. So at least this way, we can capture it and inform the user that their change was lost, as opposed to everybody thinks it went well, but really behind the scenes, data is missing. So let's see how that version might work. The benefit of this, the obvious advantage, it maintains itself. You don't have to worry about incrementing an integer or keeping track of what date it is. The disadvantage is you're storing extra information in every record and increasing the size of the table. So you really have to weigh cost versus benefit here when you're talking about concurrency control. Not every table requires it. If your table's rarely updated, like let's say, for example, you have a table that stores a list of Canadian provinces. Those don't change too often. Now, they do sometimes. We get a new territory every now and then. But for the most part, you're probably not going to have a bunch of people using that table trying to update it concurrently. So you don't have to worry too much about implementing concurrency control unless you anticipate that a lot of users are going to be accessing it at the same time. So let's take a look at adding a row version to an existing table. There are two different ways that you can do it depending on your version of SQL Server or what database type you're using. We're going to, again, add another field to our employee table so that we can maintain that concurrency control. When we alter the table, we add the new column. The name of it is timestamp, and the data type is timestamp as well. Now, normally we don't give our fields reserved words as a name. However, the convention with timestamps is that you name the timestamp field timestamp, and that sets it apart from the table data. If everything in the table is named employee something, employee name, employee address, all those things, seeing something named timestamp gives you that visual reminder that, hey, wait, this isn't part of the data. This is the concurrency control field. Different versions of SQL, some of them use something called row version instead. SQL Server has been saying that they're going to deprecate timestamp, but they never do. So row version hasn't been implemented yet in our version of SQL Server. So we're going to stick with timestamp, but you might see other examples, online in your travels where you see row version. They're pretty much the same thing. Typically, if you have a row version type of field, we call it ver, V-E-R. We're going to stick with this first one. So I'm going to add a timestamp field to my employee table. Another alter statement. Employee's getting a run for its money today. And we're going to add timestamp. So this timestamp in the square brackets is the name of the field. Now, if you don't put it in square brackets, it will still work, but it looks a bit confusing. So the square brackets are there just to denote that that's actually a field. You can put square brackets around any field name at any time. You've seen square brackets last term when we talked about aliases. If we're selecting something and you want to build an alias, we had something like this. Where we had the alias in square brackets. So we can put square brackets around names of fields. Let's execute this so that we can get a timestamp field in our employee table. So it looks like it completed successfully. Let's take a look at what employee looks like now. So here's our employee table now with the timestamps. And you can see that they are automatically populated with a timestamp. Now, we don't need to worry too much about what this value actually contains. It's kind of irrelevant to us what the value of the timestamp is. The way that this works is when we perform the read so that we can see the data, we would store the timestamp in a variable, and then when we perform the update, we include that variable in the where line so that it updates a particular employee ID, but only where our variable equals the current timestamp. Because if somebody else has updated it in the meantime, the timestamp will have changed, and the one that you read wouldn't be the same as the one currently in the table. So that gives us something that works like this instead. So we start off the same way, where red shirt starts editing this record, they perform the read, and they start changing the name Bob to Robert. Meanwhile, yellow shirt over here starts editing the same record. So they both perform the same read and get the same record for Bob Jones. Red shirt happens to save first. Now, when red shirt saves, the where line would say update the record where the ID is 4239 and the timestamp is FA9 at the end. And because nothing has changed yet, yellow shirt's still working, so nothing's changed yet, the update will happen, and when the update happens, the timestamp gets updated. So FA9 became FAA at the end. Meanwhile, yellow shirt finishes typing the address, and they try to perform the update statement, but the record that they have for timestamp FA9 no longer matches the current value of timestamp FAA. So because they don't match, your update will fail, and we can respond to the user with an error message saying your update was rejected. And he's not happy about that. He's kind of slumped over that his update was rejected. But you see what he says here, I'll try again. He's notified, and that's the difference. He's notified that the update didn't work, and then he can come back and try it again. So here's what the where line would look like. These things with the @ symbol in front are parameters. We're going to learn about them in a future class. But the where line now would compare the ID values and the timestamp values to make sure that not only are you updating the right record, but you're updating the right version of that record. Okay, let's move on to auditing requirements. Many systems require an extensive audit trail so that every change to every record can be tracked back to who and when the change was made. So systems that are sensitive, things like bank software or hospital records, stock market, things like that especially, but anything that deals with personal information or money falls under strict auditing requirements. We need to know who changed it, when they changed it. In some systems, it's even a requirement to log the before and after values of each update. Now, we're just going to touch on basic auditing requirements. We want to find out who last updated this record and when, so that's 2 fields for that, and who created the record and when. So we're going to have 2 fields for creation and then 2 fields for updates. Who, a username, and when, a date and time. So often, the insert and update procedures will include another input parameter containing the name of the logged in user. And I'll show you in a minute how we can find the name of the user in our system. So the user, the person, doesn't need to enter that information as part of the record. It will be obtained from their credentials. So insert and update statements would automatically use that username for updated by or created by fields. So typically we say updated by is the name of the user who performed the previous update. So every time you run an update command, you record the name of the current user. Whenever you run an insert command, you would also record the name of that user. And then once that is created, it would never change. So if you had a record that had created by John Smith, and then Bob Jones came along and updated that record, it wouldn't change the created by. It just changes the updated by. Now, as far as when, we almost always use the current date and time for updated on and created on. So when you run an insert statement, you pre-populate the current date and time in a created on field. And when you run an update statement, you pre-populate the current time in the updated on field. Now this slide mentions stored procedures. When we get into making database objects, you'll see how we can create procedures that kind of wrap around our insert, update, and delete statements so that we can do things like validation and auditing and all sorts of different actions that we want to verify before we actually execute things against our database. So in a few weeks, you'll learn more about stored procedures. So here's an example of adding auditing requirements to an existing table. In this example, we're adding 2 more fields to our employee table. So I've combined them into one alter statement. We're adding a field called updated by. That would be the name of the user that performs an update statement. And then we're adding another field called updated on. It's a date time field that will record the date and time of any updates. We use not null constraints to force data into those fields. You can't just opt out. We want to provide default values so that, if we're going to mark them as not null and we're altering an existing table, we have to deal with the fact that those are going to be null when we first start up. And then we also have default values so that if the user doesn't provide a value, we can pre-populate it with some default. So let's look first at updated by. It's a varchar 30 that's going to hold the username, not null, and there's a default constraint that says unknown. So if we don't provide a username, it'll say unknown. It won't leave it blank. The updated on is a date time, can't be null. Default is January 1st, 1900. Now, why would we want to default to a date that doesn't make sense when we could just default to the current date and time? Well, the reason for that is because if for some reason we have an unknown user providing an update, we don't want the updated on to, show data that is incorrect. So we don't want it to pass under the radar. So something that will stand out to us as obviously a problem is saying that something was updated in 1900. That, can show us as a flag that, hey, this isn't quite right. If we just pre-populate it to a regular date and time like today, then we would not be able to catch that as a problem right away. Now, oftentimes, if you do want to allow for anonymous users to make updates, then yes, you would want to default that to the current date and time. So really, it's a judgment call based on the rules that you're living with in the real world. By the use of defaults, older records that predate the auditing would contain these default values. So let's put this into our employee table. So I'm just going to copy that from the slide over here. I'll perform this alter statement that adds 2 more fields to our employee table, and then we'll take a look at what we've got in here. So I'll just move it over a little bit more. So now we have updated by and updated on, and you can see that these are all using the default values because none of them have been updated since we implemented the records. So now if I perform an update statement, for example, update employee, I'm just going to give Marissa Green here a raise up to $60,000. So I'm going to set employee salary to $60,000 where emp ID equals 1. So we can execute that, and we'll see how we're still getting default values here. So these defaults are operating to make sure that we're continuing to update. Now, typically what we would do is wrap our updates up in a procedure that not only performs an update, but also modifies your set command here. So whenever we perform an update, we would also make sure that we set updated by to a username and updated on to a value. So let's see what happens if we execute something like this. So now we're able to have these auditing fields that get updated. And the real benefit of this comes when we privatize our updates, and the way that we do it is we're going to write a routine, or we call it a stored procedure. It's kind of like a method almost, that if you want to update, you have to call that method and pass the parameters. It's similar to like a C# programming sort of thing, where you have to pass the parameters. We would control how the update goes. So we say, if you want to update, you have to tell us your username. And then our update would write statements for all of the fields. Now, we can do something similar for created by and created on as well. Now, another thing that we can do while we're on the topic of constraints and defaults for auditing fields is if we want future updates or future inserts, if we're talking about created by and created on, if we want future values to have different defaults than the defaults we used at creation time of those columns, then we can modify the given constraints. So because we've given these constraints names, I can access them, get rid of their old versions, and create new versions. So let's take a look at how this would work. Alter table employee and drop constraint df employee updated on. Now that constraint is the default of January 1st, 1900. After that alter table that gets rid of the old constraint, I can write another one, alter table employee, and add constraint, and I'm going to write it back. I'm going to give it the same name even, because it's a default constraint on the updated on. And I'm going to, instead of using January 1st, 1900, now any new updates would default to get date for updated on. So for indicates what field this constraint belongs to. Now we haven't had to use this before, but the reason why is because the first time I generated that constraint, it was generated as part of the field definition. But apart from the field definition, we have to specify which field this default constraint is applied to. Now, one thing to consider that I want to lead into the next lecture is what would happen if, for some reason, our database failed between these two actions. Now, you can't alter a constraint directly. You have to drop it and then recreate it. So what if the drop works, but then the add fails? Now my table's left without an employee default constraint. It would be beneficial to us to group these things together to say that if the second one fails, I want to retract the first one so that either both of them happen or neither of them happen. And that's what the next lesson is about grouping commands together so that they operate as one unit of work and it's all or nothing. We'll look at that more next time. For now, I'm going to run these two alter statements, and we'll be able to, any new records in that field will get the current date and time. We can perform something similar for when we implement created on and created by. So let's test out these new default constraints. If I perform an insert into employee, I have to provide some things. I'll provide employee number and department code and updated by, because that is not null. I think I've gotten all the not null fields in employee. Let's take a look at employees just to make sure. So I'm providing values for first name, last name, emp number, department code, and updated by. So what about the rest of them? Well, title will be null, salary will be 0, start date will be null, timestamp is self-generated, and updated on is self-generated via the default. So here's my values. Let's say we'll put in, here's a first name, here's a last name, and employee number has to be unique. Let's make it something like this. And who is performing the update? Well, I could just type my username in here, but I'm going to go on a tangent in a minute and show you how to get the username of the current logged in user. For now, I'll just type it in. one thing at a time, right? So let's perform this insert, and then we'll take a look at what we've got for that employee record. So here's my new employee, and you'll see that updated by was given the username that I typed, updated on is given the current date and time. We also were generated a timestamp automatically. We were generated an ID for the programmer's key automatically. And those other fields here were left null. So here's the example of altering the table to drop the constraint and then add a different constraint. My note here says, put these in a transaction to ensure that both succeed or fail as one unit of work. Our next lesson is going to be about transactions. So maybe after that lesson, we'll come back here and revisit this idea of grouping these commands together. Now, the last topic, recording the username. There are several different ways to get the username to be recorded in those auditing fields. If you have a client-side application, and that client-side application has user credentials, you can pass them from there. So later on in the term, we're going to learn how to get data from the app into the database. And if your app has a username or some kind of login or credential, then you can get that from there and pass that into the database too. For now, what we can do is take a look at the user that's logged in to SQL Server itself. So if we select system user, the system variable here, it's actually a function that returns something called sysname, which is a system variable. We execute that. It shows you here the name of the account that is logged in Microsoft right now. So that's one way of getting it. You can use different string manipulation to peel off the Microsoft account piece of it. So that's one way to do it. Let's take a look at another. We can view data about the current session. The session is information about the current connection. You know when you first start up SQL Server and it asks you to log in? All of that information, so server name and what time you logged in and how long you've been logged in and what server you're logged into, all of that information is stored in a system table called exec sessions. So let's select all from sys.dm_exec sessions. Now, if we take a look at that, there's a lot of stuff in here. You can see there's quite a few pieces of data about various sessions, script windows that I've opened. I've had SQL Server open for quite some time today. There's also sessions from previous days and times. You'll notice that, if we scroll over, there's quite a few fields and records here. So this is all the connections. And as you scroll down, most of the time when you're logged in directly through SQL Server, your login name would be SA, System Administrator, but there are some others as well. You can see some different places to get username from. NT_user_name is a common place to get a username from. To be more specific, you want to get the name of the user from the current session. So right now I have 57 different sessions that I could possibly get a username from. But really, I'm just interested in this current one. So in my select statement, I'm going to add a where line, where session ID equals SPID. So SPID is a global variable. You might remember earlier I said variables in SQL Server are denoted by an @ symbol. A double @ symbol means it's a system variable, as opposed to a variable created by the user. So a system variable, this is the current ID of this local current session that I've got going here. So I'm going to take that and find it in this list of session IDs. So if we execute that, this is information about this current session, when it started, the name of the host, the name of the program that is performing the connection, and et cetera, et cetera. And if we scroll across over here, there's the NT username. So if you want to be able to get the username without actually asking the user to give it to you, you can retrieve it from the connection object itself. So we could grab NT username from there for this particular session and get it here. We could store it in a variable. We'll learn about how to do that in another week or two. And then use that variable in here, like that. Okay, so we've got some things to think about as far as grouping commands together, as far as writing procedures that allow us to control how commands are executed, some things to think about variables and storing data, and writing programs so that we can take consistent actions. There's a lot more coming down the pipeline as far as learning about all of that stuff. So this is just kind of the tip of the iceberg. But this covers all of our main topics as far as concurrency control, auditing, and other real-world programming concerns for databases that are live to the public. So I hope you guys enjoyed this lesson and that you learned a lot. If you have questions about this or any other topics in the course, please send me an email or drop into any of our Collaborate sessions. Have a great time. I'll see you next time.